Right, so these are my cells in all their simulated glory. First thing they do every frame is sample their world. This first set is going to be them sensing the food signals. It diffuses through the GPU shader just on a 2D plane right now. But we can change that to be 3D, no problem. The middle set of values is their pheromone that they emit that someday could be communication. That last set is going to be their proximity to the hazard emitter. Let's call it our motivator. That's what keeps them eventually moving out from the middle. You can see that their little tendrils will indicate what kind of scent they're picking up and have the intensity and everything mapped there. The speed of the tentacles is mapped to their prediction state, so when their surprise is high, they spaz out, and when it's low, they slow down. And so once they get that sensor data, they send that, I was alluding to that predictive coding layer, and there's one neural node for each input. Along with the raw sensor data, we're generating some focus data, like telling it what an average, what the most interesting direction is for it to be thinking about. So all that stuff gets sent to the predictive coding layer. It, as it sounds, it makes predictions. It considers the last prediction that it made last frame and then generates an error based on that. And that gives us an overall accuracy level as well as a set of activities to pass on. Those activities actually get fed back into the brain to help it generate the predictions, and prediction errors as well get passed on to the neural brain. And our setup right now is two different types of neural brains. This one is, it gets sent all the input data from the sensor array, all the predictive coding data, and it sends it through a recursive neural network, and then to an LSTM, long short-term memory cells. And we can define those sizes here. So it goes from one big broad layer and gets squished down to a small layer, and then in the case of this one, it gets squished down to a concatenation layer and then put out to the outputs. The hybrid is going to be the dual STM, and those guys have one set of it gets the sensor array, the world data, plus the prediction data sent to one discrete LSTM cluster, and then the energy data from our interoception layer, plus, so it's what tracks its energy. The sensor data goes into an accumulator, not just directly into the energy, and goes through a pipeline, so that those are genetic traits that can be evolved later on. So it gives it some idea of how much energy it can expect to have in the short-term future, kind of. And so that dual LSTM type has a separate long short-term memory cell that is devoted to interpreting that data as well as the proprioception data, which is how far or how fast it's moving, turning, if there's any lateral movement from bumping, which is turned off right now, but can track that. And then those will go to a concatenation or fully connected layer that gets defined in the neural brain as well. So that's the hidden size. So those both get squished from the full inputs of sensor into spatial, and then the internal sensors into metabolic, and then those get fully connected and put out to the outputs. So right now that allows them to kind of make decisions predicted based on the weights and biases connecting all these connections from the inputs to the predictive coding layer. All this stuff gets termed as DNA in this system. It's the stuff that they're born with that tells the neurons how to interact, and that can't change throughout its lifetime. The predictive coding layer can adjust its weights during lifetime, and we keep it pretty low. It's kind of more like simulating neuroplasticity. Then if we cranked it all the way up, it would kind of learn the most boring way, or it would kind of defeat the purpose of the evolutionary approach, which is to define genomes at work, basically, and then kind of increase the complexity for them to have to work against to win. And so that kind of brings us to our evolution system, which is gotten pretty crazy. So basically, we break it down into population chunks. You can choose if you want A/B testing to see which one's more successful. We generate the generational data, we keep that in a list. We can brain dump the top 20 of any population to save that DNA. And so, yeah, we have that DNA definition to keep that separate from like genetic traits, which would be things like how fast it can absorb the energy, like I was talking about, or turn speed, how many sensors, because the sensor count can be defined up here. You can see those yellow gizmo lines kind of show where the sector divides are. So you could increase the number of those and it would be smaller sectors, and decrease it and be big chunks. You can increase the radius, and that just shows how far out it can sniff or sense. But yeah, we want that separation of those kinds of genetic traits to be things that don't really affect the innate way that the brain processes data. We want it to be more the potential outcomes that it can have when it sends those outputs. So the evolution system is eventually, right now, we have traits turned off so that we can just study the neural patterns, because I ran into problems with it, like evolving the smell rate to encompass all the food nodes at once, and it got out of hand. So we'll need to get a slower approach with that and get everything else nailed down first. So yeah, we take a chunk of the population, give it elite preservation credits to keep it unchanged, so that we can, and that way if there's a really good performing DNA configuration, then it has like a bad day kind of thing, right? One generation it spawns way over here and starts in the wrong direction, and it just never finds a sense signal to react to, right? That way, that does not just kind of get flushed out of the system. It has some kind of a temporal consideration there. It gets an amount of credit, and then if it does have that bad day, it'll lose a big chunk of that credit. But if it just has kind of a meh day, it might lose a little bit of that credit, and if it has a good day, it'll gain some. So that is what we do with 20%, and then, or well, it's defined. And then the tournament selection is just a random way of selecting parent candidates to do the crossover, which we are using a BLX alpha scheme for, which basically it sets a cap on how far it can kind of diverge from its parents. This alpha is like its exploration range. If you set it to 0, then it could explore the space, like the range within the parents' two like the average of them, so that you can't get like crazy outlying mutations. It would have to be within the bounds of those parents' uh, values. And so the bigger you make that alpha, the wider that range that you consider a possible mutation in. And so the majority of those of our population, are we're keeping the population of brain types separate in the A/B testing. We could find out a way to make that work in the future, possibly like hybrids and um, runtime evolving neural mapping kind of things. But right now, it's all separated populations. Um, but yeah, the mutation rate is also self-adaptive. So if the generational fitness change starts to plateau, the mutation rate will start to increase, and when it's in a predictable kind of trajectory, it'll start to decrease to explore that in a more granular way, just kind of a way of smoothing out the natural plateaus and peaks that you get with evolutionary algorithms. And then the bottom part of the population is just pure random selection of our agents so that we can explore more possible behavior spaces. Um, Sometimes things are just a couple of generations away. Maybe this guy is like, oh, I don't want to go over there. I haven't found another. I mean, it could be just a generation away or two from making a breakthrough genetically, right? Like, so we don't want to just completely throw away things that are non-performant. We want to arbitrarily give them a chance because we can't. I mean, we could probably find ways to consider how well they're doing outside of that. And we do have like a novelty factor that considers that. And someone we need to refactor this because it's kind of garbage right now. But in theory, that will kind of aid that problem of like novel brains that are non-performant. We want to give them a chance because they could be performant in the future and then outperform the stuff that is more basic. Um, so yeah, that is kind of the flow of the generational changes, changing that DNA structure that we're talking about. It is just like the weights and biases of our neural network setups. Um, and then the most recent addition has been adding the kind of environmental layer and then outputs that handle them digging and adding to that uh, sign distance form. It's basically taking a 3D texture, kind of the way that this guy is doing a 2D texture, storing the density data. So each one of these is a chunk that stores some amount of density data for a defined size of the world, and then these guys can alter that data, and then this mesh is put through a dual contour compute shader to figure out what kind of it can do, triangles or quads, for the deformation to fit to the density data. So all the data of the world is always being stored in that density grid. It's just any time that they update it, it gets labeled as a dirty chunk, and then it will consider it for updating the visualization for it. And these guys are just directly adding to the or subtracting from the data of that grid. Right now, like I said, we got collisions turned off. I need to consider how exactly I want to approach gravity and if I want them swimming around or crawling on surfaces and up walls and stuff. But yeah, it's getting there. Um, UI stuff, like I said, we got brain dumps. We have some. I want to get like visualization for neurons finding activation rates and stuff like that, but that's all kind of boring compared to just getting it working. Yeah, that's where we're at right now. Say bye, guys.